The universe is big, and we're going to discuss it in this option E astrophysics video. We'll be talking about Isaac Newton's model, how there was a paradox by Olber that made Newton's model wrong. Then we'll get into the Big Bang, how the universe started, and we'll also get into how the universe will end. Get ready. Isaac Newton was probably the smartest guy on the planet. His version of what he thought the universe was he thought that it was static, that none of the stars were getting any closer or farther to him. He didn't know about other galaxies at all, but he thought the stars were stationary where they were. He thought that the universe was infinite in its size and that it had been around forever and ever and ever. However, he was wrong, and we'll get to why he was wrong. A guy by the name of Olber, along with I think someone else also, but Olber's the main one you got to remember, came up with a paradox that said this about if you've got all these stars that have been there forever, then we should have a completely overwhelmingly bright night sky, which we don't. And you can think of that as if you have, here's the Earth right here, and then surrounding it is some stars. You're going to get a little bit of light from all these stars reaching the Earth. But then if these stars go on infinitely, then you're going to have tons and tons of light coming on to hit the Earth. And especially if they've been around for an infinite amount of time, they would have had all the time in the world to get there. Now, the IB will want you to show that you can do this quantitatively. That takes a little while, and if they told me to do that, I would probably just miss that question. But read about it in your textbook. Edwin Hubble, famous astronomer who later then had the famous Hubble telescope named after him, shown here, looking very dapper and smoking his pipe. He was one of the people given credit for discovering that the universe was expanding. And he did this by looking at other galaxies and at their absorption spectra, which is going to be what this is here. Certain gases are absorbing certain frequencies and causing these dark lines to be in there. When he looked at the distant galaxies, these lines were shifted to one area more towards the red end of the visible light spectrum, which showed him that most of the universe was getting bigger and bigger, which made them then extrapolate and say, well, it must have all started at a very small state. And then the whole Big Bang explanation got a lot more credit. Now, Penzias and Wilson had a very awesome telescope that was basically a giant metal horn that they could sit in, and then it would turn around to try and catch radio signals coming from different parts of the galaxy and different parts of the universe. With this, they discovered some pretty awesome stuff. They detected microwave radiation that was coming not just in a particular direction, but it was coming from everywhere. And what that turned out was that when the Big Bang happened, it didn't just happen in a particular spot, it happened where and created the universe. And so then everything that exists, all of our galaxies and stars, we're all within inside the area where the Big Bang was. So they were able to aim their radio telescope in any direction and see the remnants of the Big Bang that clearly seemed to have much stronger evidence of having happened. And this does help give us some resolution of Olber's paradox and why we don't have an infinitely bright sky, because with the Big Bang thought that it happened is that there's not an infinite number of stars. There's only a finite one, so we're not going to have an infinite amount of light hitting us. The universe definitely started at a particular time. We think it was 14-something billion years ago, and that's why we only have a finite amount of light reaching us. So we have a pretty good idea of how the universe started, but let's talk about how it's going to end. You will have, well, right now we've got this expansion, and it's getting bigger and bigger and bigger. We could have the fact where gravity eventually overpowers the expansion, slows it down, and then it comes back. That is a scenario that we would call a closed universe, with size getting bigger, and then it gets smaller. Then maybe it all starts over again. Who knows? But you could have it go and just keep going and going and going and going and going and going. That is what we call an open scenario. Or maybe it just approaches a rate of expansion of 0 at an infinite amount of time and then sort of ends frozen. That's what we call a flat scenario. This is going to depend on the density of the universe. And you can look at this definition of critical density, and if the universe has a certain density that's, let's say, below this critical, then it will just keep going and going. If it has the density as shown here, then that means it will end flat with just frozen state. But if it has a higher density than the critical one, there's much more mass in the universe than we think, then we'll end up with gravity taking over again and it shrinking back down. It looks actually that none of these are true, and that more recent evidence suggests that we have something that goes like this, and we have an accelerating universe where there's all this extra space being created between galaxies that no one really knows why, but the universe is getting bigger at a faster rate. At least, maybe not with the nearby galaxies like Andromeda, because that's coming towards us, but most of the galaxies that are farther away are getting faster and faster in their rate of fleeing from us. We want to know how the universe is going to end, and so we need to know what that density of the universe is. And so our density, is it less than the critical density, and will we end with a forever expanding universe, or is our density, the universe, greater than the critical, and will we end with a closed universe? Probably not, but in order to figure this out, we need to know the mass of the universe and compare that to the volume. And there's some problems with finding the mass of the universe. And the problem, you might have heard of something called dark matter. And of the matter in the universe, we think that dark matter, which is stuff that we can't really detect very well, or maybe at all, makes up a huge amount, maybe 80%. That could be things like neutrinos that made the news a few years ago because they thought neutrinos traveled faster than the speed of light. That would have been exciting. Unfortunately, they didn't. But neutrinos could maybe be classified as what we call WIMPs, these weakly interacting massive particles that do have mass. There might be 80 gazillion of them, but we can't detect them very well because they just don't interact with mass very well. They're very antisocial. Also, we could have things like machos, massive compact halo objects, something like a brown dwarf star, maybe a star that was a white dwarf, but it's cooling off, very hard to detect. Maybe more matter in the universe is something like that. But that's just the matter. There's also this dark energy that, if you're looking at mass energy, could be making up 70% of all the known stuff that's in the universe, which we haven't detected yet, or don't know how to detect. And so what's crazy is that maybe only, I don't know, like 5-10% of the stuff the universe is made of is stuff that we know how to measure. Everything else is all crazy and undiscovered as of yet, which makes your time in physics very exciting. Woo!